Hey everybody, Tom Cherryholmes with the FujiNet project. Here I am with the latest status update. This particular video shows that FujiNet actually has the interrupt and proceed lines connected to the SIO bus and to the ESP so that interrupt-driven network I/O is possible. This gives us a lot of advantages, but the biggest that it gives us is that we don't have to keep storming the SIO bus with consistent status calls. What can happen instead is the ESP can indicate that something needs to be paid attention to by lowering the interrupt line for just a moment, just long enough for the Atari to notice it, and the interrupt routine on the Atari can then issue a status request to get how many bytes are waiting or if the connection status has changed, etc., and go from there. This greatly increases the efficiency of network I/O, as we'll soon see here. We'll kind of do this backwards from my other videos here, and I'll just start doing demonstrations just to kind of show you the effect of all of this. But for the purposes of illustration, we will have the monitor window running on the lower portion of my screen over here so that you can see what's going on. We'll turn on our Atari and boot like we usually do from the FujiNet. We'll see that we connect to our network. Everything is as it's supposed to be. And we'll go ahead and from my file server, just to prove the point, I will take and load Plato Poll. This is a version of the Plato term software that uses the network functions, the end device, but uses polling to get all of its status information. This results in very noisy traffic. We'll see that this works, and you can see that it connected immediately, but you'll see that a whole lot of network traffic is being, traffic is being bounced back and forth, basically just looking for status requests. And this is happening so often, and the Poki is being used so often, that keyboard performance is significantly impacted. You can see, not very good. And you should be very thankful that I have turned off the Poki sound so you can't hear the inevitable buzzing too loud of what's actually going on back in the back. I think that's enough of this. We'll take and power off the unit, reset the FujiNet, and for comparison, we'll actually load the interrupt-driven version of the software. Just a moment. You'll see that it's much the same, but there is much less traffic happening. It's much quieter on the bus. And the keyboard works better. It's still not perfect, but it works a lot better. All I need to do here is just do proper write buffering. But you can see it works quite well. We'll see, for example, here, if we go load something that's requires a bit of network traffic, you'll see 3,647 bytes there as it loads the rest of that graphic data and the character set. The bits and pieces that you're seeing back are the result of the terminal program processing the data as it comes in and sending back replies to the commands that it's being sent, various echo packets. And you can see that it runs just fine. And since there is a sufficient enough buffer, we don't particularly have any speed problems. Shift stop to stop. We'll go ahead and stop this particular one. And you'll notice most definitely, even as it's sitting here, it's not constantly hammering the bus for status requests. The only time that will happen, the only time a status request will happen is if the ESP tells it that it needs to do it. Now, just for the sake of illustration here, I'm going to reboot with what I call the beeps version of Plato-Term, so you can hear the network traffic actually going back and forth. And this is accomplished essentially by leaving sound R, the sound R variable in the operating system, set to its default value of 3. If we go ahead and go here, select Plato beeps, there we go. You can hear you can hear the traffic, and you can hear the different phases of network protocol exchange. You can hear the writes of the echo packets going back and forth, and you can hear the long reads of data being shuffled back, the long strings of protocol information being received by the Atari. But you can see here that because we have a large enough buffer and sufficient enough processing power on the ESP, we're not dropping bytes. So with that, we'll go ahead and push this out of the way. And I'll show a little bit about how this actually works. So, the heart of the whole thing, essentially, is this SIO assert interrupts function. This actually gets called as part of the SIO service, which is the main loop for all SIO devices. Primarily, it concerns itself with dealing with command frame processing and marshalling off to the appropriate SIO device for processing as needed. But it also handles various other aspects as well, such as handling different type poles, type 1, type 2, type 3, but it also handles other bits and pieces like high-speed processing, switching baud rates when needed, and for modems, when the modem is active, it actually handles the main loop for handling the modem. But the thing that we're interested in here is down at the very bottom of the loop, we go ahead and call each of the network devices that we register and tell them to assert their interrupts. Asserting their interrupts right now is currently very naive, but it seems to work pretty well. We check to make sure if there is an active protocol, then we take and ask that protocol for a status update. The only reason for that is primarily so that we can get the status buffer filled, and we can check how many bytes are actually waiting for us in the receive buffer. If there are more than 0 bytes waiting in the receive buffer, then we toggle the proceed pin, which is pin 22 on our current hardware design. Wait roughly 10 milliseconds. I'm actually going to tighten that up a little bit, and bring it back high again. This works because the PIA's interrupt handling is literally edge detected, and this actually allows for the interrupt code, the interrupt handler on the other side, on the Atari, to react, give it enough time to react, and to react appropriately. Because what we're essentially doing is just giving it a little blink and say, hey, wake up, wait for a second, come here, you need to handle something. From the protocol side, really all we're doing is dealing with the receive buffer size. Now we could actually have it, I'm actually going to take and refactor this a little bit to react to a few more things, such as connections dropping, or certain aspects of certain failure modes that need to be handled. From the other side of it, if we go ahead and open a folder real quick, I'm going to go into where my Plato term build is actually happening. Inside, I need to move this, but so let's go here. I'll go to Atari, because everything I need to deal with is in here. Let's go ahead and open this up real quick, and we can see the Atari side of it. Pretty straightforward, actually. It really consists of, currently, the first pass of this is very simple. It consists of a single interrupt handler, where I expose the interrupt handler, and all it does is set trip to 01 to indicate that the interrupt happened. Bam. Then, because the interrupt handler was called by pushing state onto the accumulator, we need to take and restore that with a PLA, and then use a return from interrupt here to end the interrupt handler. This is pointed to by I/O, and we call I/O init, which actually sets up a few things for us. One of the things it does is it hooks our interrupt handler into the vector for proceed, and goes ahead and primes the interrupt to be detected by setting bit 0 of PACTL to indicate that we want to be able to service the next interrupt that comes across. We then immediately establish connection, and from that point, we spend most of our time basically flipping here. If trip doesn't get set, then we return and we don't deal with I/O main at all. However, the interrupt routine, whenever there's something that happens, this will get set to 1, and then we immediately do our status update to get how many bytes are actually waiting for us in the buffer. We then take, and if we actually do a double check here, we really don't need to do this, but I do it anyway. We just check, and if we have a read that needs to happen, we do the read, however big it is, right into the buffer, and then send the result of that directly off to the terminal machinery to deal with. And after we're done, we indicate that we have serviced the interrupt by resetting bit 0 again. Repeat endlessly. That's the gist of it right there. Done. With that, we're able to take and leverage the interrupt controls on this. We're able to leverage the interrupt lines and vastly make this particular code a lot more efficient. So there's a lot more that needs to happen. Definitely a lot more that needs to happen. But most of the firmware is really starting to firm up and come into place. Many of the things that I had theorized that were possible have been proven to be possible. And we've proven that they work, that they can be done. Now it's hankering down and implementing all of these little bits and pieces that we have to implement to get all this stuff working. And I have to tell you, I'm having a blast. Jeff's having a blast. Oscar is having a blast. Joe Arnold Moswald is having a blast. And this is probably, in my entire career as an engineer, this is easily the most fun I've ever had doing a project. And I worked on a massive smart home platform. More to come, but until next time, guys, have fun.